Swayam Prabha. Digital India. Educated India.
I welcome all of you to this lecture. Let us start this lecture with a thought process from Albert Einstein, one of the greatest scientists of 20th century. He says the true sign of intelligence is not knowledge, but imagination. It is a very profound and practical message what he has given, because without imagination one cannot really harness new knowledge with plethora of intelligence with a person. Hence, it is important for us to harness and use our imaginary power for harnessing the new knowledge. Let us look at the performance of the rocket nozzles, and because we need to see how good it is as compared to the ideal one. For that, 5 performance parameters are generally being used by the designer, and these are basically isentropic nozzle efficiency, discharge coefficient, mass flow coefficient, and thrust coefficient effectiveness, and combustion efficiency. And let us look at the expansion process in a TS diagram. If you look at when expansion is occurring in a nozzle, this is the ideal one and this is the actual one. You can see that there is a change in this is change in entropy. So, this is correspond to actual. So, therefore, we can define the nozzle efficiency as ST2 minus HE, that is the actual one for the pressure ratio of PT2 by PE divided by ST2 minus S2 HES, this corresponding, this is the ideal correspond to enthalpy. And if I assume the Cp to be constant, so therefore, I can write down the isentropic efficiency as the TT2 minus TE divided by TT2 minus TES. And if you look at this is basically VE square divided by 2, this is VE square divided by S2, and this is nothing but your isentropic efficiency. And this isentropic efficiency, as I told, I can write down this VT square divided by 2, and ST2 I can take this Cp as a constant and TT2 I will get, basically if I take this bracket out, then I will get Cp TT2 in the bracket 1 minus TTS by TT2. If you look at this is the isentropic flow, so therefore, we can really express that in terms of pressure ratio PE divided by PD2 power to the gamma minus 1 divided gamma, and in place of Cp I can write down that is basically gamma R divided by gamma minus 1 and TT2. You can see that from this I can get very easily from experiment, and I can calculate with theoretically, provided I know the pressure ratio of PT2 by PE, and of course, the chamber temperature or the combustion chamber temperature TT2 and gamma. So, this is basically theoretical one, you can say this is theoretical or ideal one, and this is your actual one, and these values will be varying something around 0. These values will be varying something 0.9 to 0.98. So, let us now look at discharge coefficient, and discharge coefficient is basically comes out due to the boundary layer effect and then other things, and we know that actual effective flow area of the nozzle always slightly less than the geometric area due to presence of boundary layer on the wall of the nozzle. So, therefore, it is we need to define discharge coefficient, that is equal to actual mass flow rate divided by the ideal mass flow rate. If you look at mass flow rate, I can write down rho E A E V E, that is the actual mass flow rate, divided by the rho E S A E, A will remain same, and V E S, and this is corresponding to isentropic or without any isentropic flow and without any boundary layers, right. So, I can write down this is basically T S and V E, and this is basically T E and V S, and I can write down T E S by divided by T root over I S, and this you can see that I S is basically this root over I S I can write down is V E I N. I can say this is basically I N, whatever I have defined, V E by V E S, right. So, and discharge coefficient C D depends on the Reynolds number and P T 2 by P E, that we have already aware that this C D, if you plot it, C D is a function of pressure ratio. You can see that in the subsonic flow this is not changing much due to the Venturi effects in the CD nozzle, and after that it goes on decreasing because of the V E will be different than the V S because of losses, and it till it attains the choked flow conditions. And the mass flow coefficient C M we have already defined, that is basically C M is equal to m dot P divided by P C by A T, and this is you can get from the experiments and also theoretical values and find out how good it is. And mass flow coefficient can be, as I told, can be obtained from the experimental data and documented in form of design chart, so that it can be utilized and you can find out how good it is from the ideal one. And we already discussed about thrust coefficient effectiveness, that is equal to ratio of thrust coefficient actual divided by thrust coefficient ideal one, and thrust coefficient the actual one you can find out from experiment by conducting by determining the thrust and the chamber pressure and the throat area, and the ideal one we can get from knowing this pressure ratio and gamma and area ratio and atmospheric pressure. We have already discussed about this thing, and you can find that this actual practice, in practice the actual CF is around something 0.98 of the ideal values, but these values will be varying as such because you will get these values can be EF, you can get in the range of something 0.92 to 0.98. And the another thing which is being very much used, as I told earlier, that is the combustion efficiency, which is the ratio of characteristics at actual velocity at actual condition to the ideal characteristics velocity, and actual characteristics velocity can be obtained by the conducting experiment by measuring the mass flow rate of propellant, chamber pressure, and of course the throat area under choked condition. And the ideal one you can estimate very easily by knowing the chamber temperature, thrust chamber temperature, and molecular weight, and also the gamma, and these you can get from basically from equilibrium calculations, and these values will be varying something around 9.5 to 0.99. The combustion efficiency varies, and generally people always try to achieve value of 0.99. So, these are the parameters which are being used for evaluating the performance of the rocket nozzle engine, and we will be discussing about how does the exhaust nozzle velocity affects the flight performance of a rocket vehicle. rocket vehicle, if you look at it, basically a vehicle propelled by a rocket engine. It can be missile, it can be spacecraft, it can be any other vehicle which is being propelled by the rocket engine. So, when it is subjected to the thrust, it will be in motion provided it overcomes of its own inertia, gravity, and of course, several other forces which will be acting on it. A question might be coming in your mind, what are the forces that are acting on a rocket vehicle during its flight? Apart from the thrust being exerted by the rocket nozzle, it will be also experiencing the gravitational force, drag force, lift force, and even centrifugal force and Coriolis forces, and the forces applied by the control surfaces. And as a result, there will be moment, and the flight of a rocket vehicle or the flight path of a rocket vehicle will be three-dimensional in nature. But for our present analysis, we will be considering two-dimensional plane in which a rocket engine is flying. Let us consider this is a rocket engine, and this is possible to be flying in a two-dimensional or rectilinear plane provided the no moment is acting on it, and this is not realistic, but however, for simplicity we are considering here. And keep in mind that this having a center line, right, if you look at the center line will be passing through like that, and this is making an angle theta here, and of course, this we can say this is the CG of this rocket engine. And when the high pressure and high temperature gas due to the burning of propellant will be expanded through the nozzle, it will be having certain exit velocity or exhaust velocity V e, it will be producing a thrust, and this thrust will be making the vehicle to propel provided it will be overcoming the drag force and also the gravitational force, and other forces we are not considering being small, and also we are considering the flight path to be in a plane which is not possible, but we are considering for our simplicity. So, if you look at the forces what will be acting over here is various, and that forces will be making the vehicle to move with a velocity v along the direction it is shown. So, let us say that what are the forces are acting, and then for that of course, we will be considering, as I told, the various forces like thrust, the drag, and also gravitational. So, this is your thrust force which is acting, this is your drag force, this is your drag force, and this is your gravitational force due to gravity. And keep in mind, this is the angle your theta, and this angle will become theta. So, we will be considering a force balance on this rocket vehicle along this axial direction, because, or rather along the direction of its motion. And keep in mind that during this, the mass of the vehicle will be receding due to the consumption of the propellant, and which will be getting expanded in nozzle and moving out of this rocket engine. So, by considering a force balance, we can derive a rocket equation, And let us look at the force balance along the direction of its motion or along the axis of this vehicle. So, that is equal to basically let the m be the mass of your vehicle, instantaneous mass of the vehicle, that is m, instantaneous vehicle's mass, and it will be subjected to acceleration provided the thrust is overcoming the drag and the gravitational force. Keep in mind that generally when it is taking a lift kind of things from the surface, generally the thrust force which is applied on a rocket engine will be at least 2 times, 1.5 to 2 times of the weight of the engine. That is the thumb rule, and to have some tangible acceleration, otherwise there will not be much acceleration in that. And dV by dt, that is the mass of instantaneous mass of the vehicle into this acceleration, is equal to F minus the gravitational force along this axial direction will be m g cos theta minus the drag force, and drag force in the along with the direction of the force. Keep in mind that the drag force can be of various forms. It can be form drag, it can be skin friction drag, it can be base drag, but however we are considering here the total drag due to the vehicle motion what is happening, and this drag will be dependent on also various parameters, namely the velocity of the vehicle, it will be dependent on the surface area and density of the air through which it is moving. And this is if you look at this gravity, this is g which is gravitational acceleration. This is basically at any time. Keep in mind that along with the altitude, the gravity will be changing and being maximum at the sea level, and it goes on decreasing. So, if you look at this thrust, and this is your thrust, and thrust F, we know that it will be equal to ISP into G naught into the mass flow rate of propellant. This is mass flow rate of propellant, and let us say this is your equation 1, and then mass flow rate of propellant will be equal to change in the mass of the vehicle, that is m dot p will be equal to minus dm divided by dt. And keep in mind, due to the propellant getting consumed and going through the nozzle, the mass of the vehicle will be also receding. Therefore, this negative final mass minus the initial mass divided by the delta t time, and the final mass always will be the less than the initial mass. So therefore, when you will substitute this thing over here, we will get, then we can write down this F is equal to ISP G naught dm by dt with minus sign, this will be minus. Okay. And this equation we can call it as A, equation 1. By using equation 1 and A, we can have m dv by dt is equal to ISP G naught, this will be having minus sign, dm by dt minus mg cos theta minus d. So, if I divide this mass both the left hand side and right hand side, if you look at this is 1, this is 1, then I can write down this as dV by dt equal to minus ISP G naught 1 by m dm by dt minus g cos theta minus d by m. By integrating this equation, let us say this is your equation 2, we can get basically, if I will do this dt over here and integrating from 0 to Tb, similarly I can integrate this here 0 to Tb, this way I can to Tb and dt 0 to Tb. So, I will get basically change in velocity of the vehicle, which is nothing but your V f minus V initial, V final minus initial is equal to, and keep in mind that ISP and G naught will not be changing with respect to time. So, I can write down this ISP G naught and dm by m, and this mass will be changing from initial mass to final mass minus g cos theta minus m dt. This is your equation 3. Keep in mind that these are 3 terms which are coming, and Tb, as I told, is burn out time, and I have already told you Mi initial mass of vehicle, Mf is final mass of vehicle at the end of burnout. So, let us look at how we can integrate this and what are these terms considered to be. That means, this change in velocity of the vehicle is affected by the 3 terms. This is one term, and then another this is term, that we will see in the, and with this we will stop over. Thank you very much.